There are 5 contributors to measurement error: repeatability, reproducibility, stability, bias, and linearity. Measurement error is a term used in statistics that identifies the net effect of all sources of measurement variability that cause an observed value to deviate from the true value. Once accuracy and sensitivity have been achieved, it is often desirable to determine the repeatability and reproducibility. There are 3 methods to quantify repeatability and reproducibility: the range method, the average and range method, and the ANOVA method. Let's address the range method first. The range method is a simple way to quantify the combined repeatability and reproducibility of a measurement system. To separate reproducibility and repeatability, the average and range method or the analysis of variance method must be used. The average and range method computes the total measurement system variability and separates it into repeatability, reproducibility, and part variation. The average and range method was very popular for many years, but has recently been abandoned in favor of the ANOVA, primarily due to the ease of computers and availability in performing the ANOVA calculation. The analysis of variance method is the most accurate method for quantifying repeatability and reproducibility. In addition, the ANOVA method allows the variability of the interaction between the appraisers and the parts to be determined. ANOVA allows us to separate the total variance into various categories: part variance, part effect, appraiser effect, and replication error. Each component is additive and sums to the overall measurement error. ANOVA can easily be performed using any statistical package. Data is typically entered in a stacked format. Column 1 is the inspector, column 2 is the part, column 3 is the measurement attempt, and column 4 is the measurement. A partial format is shown above. The setup of the experiment is rather straightforward. A small collection of parts are randomly selected and numbered. 3 inspectors are chosen and asked to randomly select and measure the parts using the same instrument. Once all 3 inspectors have measured all parts, repeat the process such that 2 sets of measurements for each part and each inspector have been recorded. Let's consider this example. The ANOVA output is shown here. Determination of the values in this table can easily be accomplished using statistical technology. We will hit the highlights, but will instead focus our attention on the interpretation. First, note the mean sum of squares of the error term, MS. It is 0.2581. If we take the square root of this number, we get the repeatability, 0.5081. We see that repeatability, otherwise known as the error variance, contributes 41.73% of the total variation in this data. Reproducibility is the variation among inspectors, which contributes 0.08% of the variation in the data. Furthermore, notice that the calculated F for the inspectors is 1.0185 compared to an actual F critical of 3.68 at alpha 0.05. If the calculated F is less than the critical F, we cannot reject the null hypothesis that there is no difference among inspectors. In other words, any reduction in measurement variation cannot be realized via the inspector. You will also notice that there is no significant contribution between trial. This means that the inspector measures each part the same way. Total measurement contribution is repeatability variance plus technician variance, which equals 0.08% plus 41.73% for a total of 41.81%. Repeatability variation must be looked into if we wish to reduce the overall R&R variation associated with this activity. Process variation accounts for 58.20% of the total variation in the data. In this case, the calculated F is bigger than the critical F value. So we must reject the null hypothesis of no difference between parts. A deeper investigation of the data compared to the specification would be needed to determine if there is too much process variation. Bias is the difference between the output of the measurement system and the true value. In the formula here, N is the number of times the standard is measured, X sub I is the ith measurement, and tau is the specification value. Bias is usually reported as a percent of process variation or as a percent of tolerance. Bias is negative when the gauge underestimates and positive when the gauge overestimates. Bias studies start with an artifact with a known value. We measure the part using the measurement instrument. More measurements improves our confidence of the accuracy. No matter how robust our gauge or our method, there will be bias. Only if the bias is statistically significant should we be concerned. The significance is tested using the t-distribution. As the number of measurements increases, the t-test becomes more conclusive. Linearity is an extension of the bias parameter. Linearity is found by obtaining reference part measurement values through the operating range of the instrument and plotting the bias against the reference values. A pool of data from a lot of 10 to 15 parts each measured 5 times is needed. The percent linearity is the slope of the best fit straight line through the data points. Linearity is the product of slope and the process variation. We can use the best fit line to estimate the bias at any point. The stability of a measurement instrument refers to the ability of a measuring instrument to maintain an optimal working order over time. This could be determined by developing records of calibration that would record the as-found condition as well as the frequency. Quality professionals can leverage this information to adjust the calibration schedule of the instrument based on the stability. If the instrument is found to be in acceptable working order at a frequency of 6 months, then an opportunity may exist to extend the interval to a year. This will free up resources to work on more urgent issues.